A primary goal of research studies is to understand general principles based on a limited number of observations. Testing hypotheses about a population of values after observing a relatively small random subset of these values provides an important step toward meeting that goal. Yet another inferential tool, the confidence interval, can be even more informative as we seek to understand a population that we cannot observe. In this video, we will look at the general procedure of confidence interval construction, then exemplify this method by constructing a confidence interval for a proportion. Why use confidence intervals when we already have the inferential hypothesis testing method? I'm going to answer that by illustrating the results of each method. Here's a null hypothesis that would be quite relevant for a matched pair design in which two matched participants are randomly assigned to treatment and control conditions. The null hypothesis states that in 50% of the pairs, the treatment participant will outperform or improve more than the control participant. Think about what that means. This means that whether the treated participant or the control matched participant shows the most improvement can essentially be decided through a coin flip. This is not a ringing endorsement for the treatment. Thus, we introduce a statistical alternative hypothesis that is in keeping with our research hypothesis. This states that there is a greater chance that the treatment participant will improve than vice versa. In other words, the treatment works, at least for most participants. We draw a sample to observe, build a binomial distribution using the null hypothesized value of pi equals 0.5, then determine if our observations are far enough in the upper tail of the distribution to be able to reject that null hypothesis in favor of the alternative. Suppose we calculate a p-statistic of 0.021, and that we're using a nominal alpha of 0.05. We can conclude that indeed more than 50% of those provided the treatment will improve. This is the type of outcome we hope for when we test hypotheses. The confidence interval can provide a more specific outcome. For example, with a confidence interval, we might conclude that in the population, the proportion of individuals who could improve with treatment is over 0.71 or 71%. That finding, that more than 71% of those provided the treatment will improve, is a more specific and more profound finding than that more than 50% will improve. Before turning to how we construct a confidence interval, let's pause to recognize that these intervals typically come in three flavors, and that each type of interval is associated with a different format of the hypothesis test. If we might test an alternative hypothesis to see if the proportion improved is above some value, then that will correspond to the construction of a lower bounded interval that tells us the specific value. So in this case, 0.71 forms the lower bound of the proportion of the treatment members of each pair that would improve. A hypothesis test to determine if the proportion is less than some value corresponds to an upper bounded confidence interval. A two-sided alternative hypothesis, when we want to determine that a proportion is different than a specified value, such as 0.5, will correspond to a confidence interval that has both a lower and upper bound. This is more likely to be appropriate in exploratory studies rather than theoretically motivated studies that are the hallmark of science. The choice of which of these types of intervals is most appropriate becomes obvious in the context of research. In the example to follow, we are seeking to show that the treatment will work and to determine how well it works from the standpoint of how many could improve with the treatment. Thus, we will seek a lower bounded confidence interval. There are several ways to construct confidence intervals, but one of the most important ways that has wide applicability is the inversion method. This is the method I use most often and what I'm going to focus on in this course. First, We set the nominal type 1 error rate, that is our maximum tolerance for a type 1 error, just as we do when we test a hypothesis. Indeed, we're still going to do hypothesis testing, but rather than focusing on a single hypothesis, we're going to test all possible hypotheses. The symbolism here is that omega is a placeholder for whatever parameter is of interest. In our current series, we would replace omega with pi because we're focusing on the population proportion that finds benefit from a treatment. But we could use any parameter. We're also using c as a placeholder, this time for the specific value we want to propose in our hypothesis test. Rather than sticking with a single value, such as c equals 0.5, we're going to let c range across all possible values from negative to positive infinity. This provides a general range, but sometimes, such as in the current context, we know that c is only possible in a more restricted range. We're dealing with proportions here, so that range can only be from 0 to 1. We test all possible hypotheses, rejecting some, retaining others, and the set of retained hypotheses will form a 100 times 1 minus alpha % confidence interval for the parameter. For example, if we set the type 1 error rate at 0.05, putting that in for alpha in this formula, we will construct a 95% confidence interval. Here's an example. A random sample of 15 registered voters were asked if they planned on voting for the school bond referendum. As of the date of the survey, 12 voters said yes. In our sample at this current time, we have 12 out of 15 yes votes, or 0.80 of the sample. This number is going to play two important roles. It is a description of our sample using a maximum likelihood estimate of the population proportion. Description is about what we actually observe in the sample, and inference is about using this observation to make our best guess about the population parameter that we can never really know for certain. To construct a confidence interval for that parameter, we're going to establish a tolerance for errors, setting the nominal rate at 0.05. We know that we will need to test all possible hypotheses, but we have to start somewhere. So why don't we start with the most common null hypothesis, which will correspond to the treatment not working? That is, set pi to 0.5. The alternative hypothesis is that the treatment does work, so pi is greater than 0.5. Now we're going to use the null hypothesized parameter of 0.5 and the sample size of 15 as the two parameters to construct the binomial distribution. Here it is in graphical and statistical form. To calculate the p-statistic, we must sum the probabilities for the observed value of 12 and those that are even more inconsistent with the null hypothesis in the direction of the alternative hypothesis. That is, those values that are 12 and greater than 12. This yields a p-statistic of 0.01758. Now this is less than the nominal level of 0.05, so what can we do? We can reject the null hypothesis. And we can determine that in the treatment, the prevalence of yes votes is greater than that of no votes. For those who are testing a single null hypothesis, this is the most common one for dichotomous data, and this would be the only hypothesis tested. But we're building a confidence interval, so we need to entertain additional hypotheses, such as this one. Can we reject a null hypothesis of a population proportion of 0.6 yes votes in favor of an alternative hypothesis that states the proportion will be greater than 0.6 or 60%? Again, we build a binomial distribution. This time the parameters of the distribution are pi of 0.6 and n of 15. There is something important to notice here that is common fare with nonparametric methods. Not only has the distribution shifted to the right, but it has also changed shape. If you look closely, you'll notice that it is no longer symmetrical. If you think about using the normal distribution as a model in the traditional parametric land, when we change the hypothesis about the mean, we shift the distribution but leave everything else about it intact. And to do so, we must impose conditions. For the binomial distribution, however, if pi changes, so does the shape of the distribution, and it happens naturally. Our hypothesis test reflects this new distribution without imposing any additional conditions. We follow the same procedure of summing the probabilities from 12 through 15, and the p-statistic is now 0.09050. That exceeds our type 1 error tolerance. Thus, we cannot reject this null hypothesis. We retain it. We have found a value of pi, 0.60, that we want to put in our confidence interval. How about this hypothesis, pi equals 0.56? Should we put that in the interval? Here's the distribution. Summing the values that exceed and are equal to 12, our observed number of yes voters, we can calculate the p-statistic. We cannot put 0.56 in the interval. It is rejected. All right, what about 0.57? We construct the new distribution. This one is only slightly different than the previous one because we only changed pi a little. Nonetheless, look what happens when we calculate the p-statistic. It is greater than 0.05, so we must retain 0.57. We are done. Wait, didn't I say that we must test all hypotheses from negative to positive infinity? I did, but we have taken a shortcut. First, we know that we can reject 0 and below and 1 and above. The probability of selecting a voter who will vote yes must be between these values. Then we tested a few values and quickly zoomed in on the border between rejection and retention. At that point, we know all the values that will be rejected and all that will be retained, so we can make a conclusion about all possible values of C without actually testing every value. And here's a secret. There's an even better shortcut. We can use statistical software that will do all of this in the background and give us the results. But what we're doing here in this video is learning what it is doing in the background so that we can better understand confidence interval construction. Here was the original example. We began with a population that was too large to observe. We randomly selected a much smaller sample, in this case only 15 voters. We determined the success rate for the sample. This same value is also our best guess about the population success rate, though if we stop there, we cannot have any confidence in this guess. So therefore, we took another step and constructed a 95% confidence interval for the population proportion. This provides more information than a single hypothesis test, and with this information in hand, the school district can determine whether they should hold additional information sessions to build support for the school bond referendum, or whether they are content with 95% confidence and believe they are in a steady state. By this, I mean opinion can vary from day to day, but maybe they believe that it's not going to vary between now and voting day. The confidence interval is not only about generalizing to the population, but it also contains ecological generalization. If the population changes, or if something about the ecology changes over time, we can no longer rely on our estimates. Here's our review. A confidence interval can be constructed by inverting all possible hypotheses tests. A confidence interval provides more specific information than a single hypothesis test. Reporting both the hypothesis test and confidence interval includes a redundancy because the interval provides all hypothesized values that are retained given the observations. If you tell me that a value is in the confidence interval, I can tell you that hypothesizing this value will lead to retention rather than rejection. Similarly, if a hypothesis is not in the interval, then using the observations to test that hypothesis is going to result in a p-value less than the nominal alpha, and the hypothesis can be rejected.